All right, so now we can talk about vectors in the plan. In this section, we're going to have a lot of definitions before we get to working some of our problems. We got to set a foundation for vectors, what we can and what we cannot do, and then we're going to work out some problems and everything. So many quantities in geometry and physics, such as area, volume, temperature, mass, and time, can be characterized by a single real number scaled to appropriate units of measure. These are called scalar quantities, and the real number associated with each is called a scalar. Other quantities, such as force, velocity, and acceleration, involve both magnitude and direction and cannot be characterized completely by a single real number. So, in terms of vector quantities, we talk about scalars, what we can and can't do. We talk about what we can do with them because they have direction and magnitude to determine if two vectors are equal and everything. So a directed line segment is used to represent such a quantity as shown. So we have an initial point P and a terminal point Q. So we know that we are going from P to Q because of the arrow. The arrow tells us what direction we're going. The directed line segment PQ has initial point P and terminal point Q, and the length or magnitude is denoted two vertical bars, PQ, two vertical bars. Sometimes we will denote this with an arrow on top that will kind of tell us what direction we're going. Other times we're not going to write that. So just be aware they both can help us out. Directed line segments that have the same length and direction are equivalent, as shown in this other picture. Doesn't matter what we're doing, we have to just be able to see that they have the same length, they're going in the same direction, therefore they're equivalent. They don't have to be 100% on top of each other to be equivalent. That's why we have the other cases of figuring out magnitude and direction. So the set of all directed line segments that are equivalent to a given directed line segment PQ is a vector in the plane and is denoted by V equals PQ with an arrow above it. In typeset material, vectors are normally denoted by lowercase bold-faced letters such as U, V, and W. When written by hand, vectors are often denoted by letters with arrows above them, such as U with an arrow, V with an arrow, and W with an arrow. Like I just said, our most common way that we're going to see them is U, V, and W. Be sure that you understand that a vector represents a set of directed line segments, each having the same length and direction. That way, they're not always just one vector, it's actually multiple vectors. So when we're given a vector that looks like the one below, where we start at the point 0, 0, it is said to be in standard position because we start at 0, 0, and we go to somewhere else. I don't care where we go, as long as we go somewhere, it's in standard position because we started at the point 0, 0. So we're going to have component forms of our vectors. So V would be denoted by V1, V2. V1 and V2 are called the components of our vector V. If both the initial point and the terminal point lie at the origin, then V is called the zero vector, denoted by a bold-faced 0, which is equal to 0, 0. So this definition is going to imply that two vectors, U equals U1 and U2, and V equals V1, V2 are equal if and only if U1 equals V1 and U2 equals V2. However, it may not always be that way, but understand we could see other variations. The following procedures can be used to convert directed line segments to component form or vice versa. So if you have a point P, P1, P2, and a point Q, Q1, Q2, are the initial and terminal points of a directed line segment, the component form of a vector V represented by V1, V2 is PQ equals Q1 minus P1 and Q2 minus P2. Moreover, from the distance formula, you can see that the length, or what we call as the magnitude of V, is given by magnitude of V equals the square root of Q1 minus P1 all squared plus Q2 minus P2 all squared. Well, if we know that Q1 minus P1 and Q2 minus P2 was V1 and V2, it's really just the square root of V1 squared plus V2 squared. Second, if V equals V1, V2 can be represented by the directed line segment in standard position from P00 to Q V1, V2, the length of V is called the norm of V. So anytime that you see this right here, it's also denoted as the norm. So if the norm of V is equal to 1, then V is called a unit vector. Moreover, if the magnitude of V is equal to 0, if and only if V is the 0 vector. In other words, there's no way else we can get V equal to 0 unless it is the 0 vector. Otherwise, it will have a value. 1 is our special case that gives us a unit vector. Just like with everything else, we got to have some definitions for vector addition and scalar multiplication. We can't just go out there and do whatever we want to. We have rules. So let U equal U1, U2, and V equal V1, V2 be vectors, and let C be any scalar. The vector sum of U and V, so U plus V, we're going to go component for component. U1 plus V1, and then U2 plus V2. The scalar multiple of C and U is the vector C times U, which is equal to CU1 and CU2. The negative of V is the vector negative V, which is actually equal to -1 scalar times V, which is just equal to negative V1, negative V2. The difference of U and V, we have to think about it in terms of scalars. So it's U minus V is actually U plus the negative of V. So it's U1 minus V1 and U2 minus V2. So here we're told let V be represented by the directed line segment from 0, 0 to 3, 2, and then let U be represented by the directed line segment from 1, 2 to 4, 4. We want to show that V and U are equivalent. So in order to show that they are equivalent, the first thing we need to do is form the vectors. So U is going to be the vector 3 minus 0, 2 minus 0, which is the vector 3, 2. V is the vector 4 minus 1, 4 minus 2, which is the vector 3, 2. Notice they're the same exact vector, so that means that they're in the same direction. So therefore, we need to make sure that they have the same magnitude. So the magnitude of U in this case will equal the magnitude of V, which is the square root of 9 plus 4, which is the square root of 13. They equal each other because they are mathematically the same exact. So that's what we're having to check there, is to see which one is which. So geometrically, the scalar multiple of the vector V and the scalar C is the vector that is the absolute value of C times A as long as V. So we can see different cases of this sort. So if C is positive, CV has the same direction as V. If C is negative, CV has the opposite direction. So sometimes we might have a need to find a unit vector or a vector in the same direction or the opposite direction. We can do different things. We can have V, we can multiply by 1/2, multiply by 2, multiply by negative, multiply by -3 over 2. We can do those simple operations because of our scalar C. Now, when we're adding two vectors, there's different ways of doing it, but the most common way is to use the parallelogram method. So the sum of two vectors can be represented geometrically by positioning the vectors without changing their magnitudes or directions so that the initial point of one coincides with the terminal point of the other. So basically what we're saying is, given two vectors, U and V, we can write them from tip to tail. So if I took this u vector or this v vector, and basically what I'm doing is I'm going to put the tip way up here, which is what we've done right here. We can then, by the parallelogram method, we can create this dashed line here and here by just moving u and v. That's what we've done over here in this third case. The piece this long piece in the middle here, that is what we call as our resultant vector, or in this case, the resultant vector is u plus v. So by finding that resultant vector, that'll actually tell us the vector whose sum is u plus v. So the vector u plus v is called our resultant vector. It is the diagonal of the parallelogram, having u and v as its adjacent sides. And this slide right here will show geometrically what's going on. Ultimately, our goal is to have a full vector. This one was using subtraction. Addition versus subtraction, they both will give us the exact same style. It does not matter. We can still use the same exact method for it. Scalars don't really affect us too much. Well, all we're doing is really just moving stuff and using some algebra to get there. So some properties of our vector operations. So let u, v, and w be vectors in the plane, and let c and d be any scalar. So u plus v is equal to v plus u. Commutative property, it doesn't matter which way we add them. U plus v in parentheses plus w is equal to u plus v plus w. Associative property still holds. U plus 0 equals u is our additive identity. U plus a negative u is equal to 0 is our additive inverse. C times du is equal to cd times u. That's our scalar multiple property. C plus d times u is equal to cu plus du. So you can always multiply it out with the distributive property. C times u plus v is equal to cu plus cv for our distributive property. 1 times u is equal to u, and 0 times u is equal to 0. Those are our multiplicative identities of multiplicative identity is 1. The 0 multiplicative property is the other one. So any set of vectors that satisfies the 8 properties before is a vector space. The 8 properties are the vector space axioms. So this theorem states that the set of vectors in the plane forms a vector space. So let v be a vector and let c be a scalar. Then the magnitude of cv is equal to the absolute value of c times the magnitude of v. So anytime that you have a scalar, you don't have to incorporate the scalar inside of your magnitude. You can just multiply by the absolute value of it in the end. So in many applications of vectors, you sort of find a unit vector that has the same direction as a given vector. The next theorem will give us a procedure for doing this. So if v is a non-zero vector in the plane, then the vector u is equal to v divided by the magnitude of v, which is equal to 1 over the magnitude of v times v. This one will have length 1 now and is also in the same direction as v. U is called a unit vector in the direction of v. This process of multiplying v by 1 over magnitude of v to get a unit vector is also called the normalization of v. So we can still do different things with it. Sometimes we just got to pay attention to the wording on what we're actually finding. Sometimes it might say unit vector, sometimes it might say normalize. So the unit vectors of 1, 0, and 0, 1 are called the standard unit vectors in the plane and are denoted by I equals 1, 0 and j equals 0, 1. If we notice in this figure down here, it tells us how we can find it. They're both starting at 0, 0. I goes on the x-axis, j goes on the y-axis. So you can kind of always think about that your vectors are always I and j, or ijk if we go into 3D or whatever. So v can be represented as v1, v2, which is v1 comma 0 plus 0 comma v2, which is v1 times 1, 0 plus v2 times 0, 1. or v1i plus v2j. So when we write it in terms of this last piece, the v1i plus v2j, we're creating the linear combination of I and j. The scalars v1 and v2 are called our horizontal and vertical components. In your physics class, you probably talk about breaking down your force vectors into your x and y components. That's the same theory of what we're doing here. So we are told here to normalize the vector v equals 1, -2, -2. That is, we want to find a unit vector that has the same direction. So the first thing we need to find is the magnitude of v, which is the square root of 1 squared plus -2 squared plus -2 squared, which is the square root of 1 plus 4 plus 4, which is the square root of 9, which is 3. So in other words, our unit vector u is equal to 1 over 3 times 1 -2 -2, or 1/3, comma, -2/3, comma, -2/3. This will be our normalized vector v. So the next problem we have, we're told the vector v has the initial point p equals 722 and q equals 272. We're told write the vector v as a position vector, then write the answer in terms of the standard basis vector, that is, write it as ai plus bj plus ck. So first we need to find our vector v before we can do anything. So our vector v is really q minus p, which is equal to 2 minus 7, 7 minus 2, 2 minus 2, which is -5, 5, 0. So that is our v as a position vector. As a standard basis, this is -5i plus 5j plus 0k would be our basis vector here. If you have this case right here, you could write this as -5i plus 5j, and it would be the same thing. So the next thing we're told is use the vector v of 5, -1 and w as -3, 1 to find the magnitude of 4v minus w. Well, in this case, we want to go ahead and find 4v, which is equal to 20 and -4, minus w is 3, -1. So then if we were to combine these two, in this case, we're actually just going to 4v and minus w, we would be combining them. So therefore, this would now be a plus between them. So 23 and -5. Now we need to find the magnitude. So that's the square root of 23 squared plus -5 squared, which is the square root of 529 plus 25, which is not a perfect square root because this is the square root of 554. So don't let it confuse you on what we're doing. We're still using the exact same style, just build it up. So What I would do with this one, I would make this u plus 2v minus 6w. So my u doesn't change, so it's 3, 2, negative 9. 2v is 12, 0, 4. And then minus 6w is 30, 42, negative 24. So now I'm going to combine all of these. So I'm going to get 45, 44, and negative 29. So just build them up. As soon as you find a minus, all of this turns into a plus on the outsides at that point. So we're told use the vectors u equals 1, 1, negative 6, v equals 3, 0, 7, and w equals negative 3, negative 1, 2 to find the magnitude of 2u minus the magnitude of v plus the magnitude of w. So let's start with this. The magnitude of u is the square root of 1 squared plus 1 squared plus negative 6 squared, which is the square root of 38. The magnitude of v is the square root of 3 squared plus 0 squared plus 7 squared, which is the square root of 58. The magnitude of w is the square root of negative 3 squared plus negative 1 squared plus 2 squared, which is the square root of 14. Now don't forget, we had 2u up here, so what we need to do is multiply this by magnitude of 2, which is here. So therefore our answer would become 2 root 38 minus root 58, because we needed a minus in front, and then plus square root of 14. So that would be our answer for this type of problem here. So we're told to normalize the vector w of negative 3, negative 1, 2. Then we want to find the unit vector in the opposite direction of w. Okay, so let's build this one up. So the magnitude of w is the square root of negative 3 squared plus negative 1 squared plus 2 squared, which is the square root of 9 plus 1 plus 4, which is square root of 14. So our unit vector u is the vector negative 3 over root 14, negative 1 over root 14, and 2 over root 14. So we normalized. Now it says find the unit vector in the opposite direction. So opposite direction means we would have 3 over root 14, 1 over root 14, and negative 2 over root 14. So opposite direction means minus u, is what that really means. So for this problem, we're told use the vector u equals 6i minus 5j plus 14k, v equals 7i plus 2j minus 5k, and w equals 6i plus j plus k to find the following. So in this case, u plus v is going to be 13i minus 3j plus 9k. That's doing component for component, adding my I terms together, my j terms, then my k terms to get this. Now the magnitude of w is the square root of 6 squared plus 1 squared plus 1 squared, which is the square root of 38. So u plus v over the magnitude of w is 13 over the square root of 38 times I minus 3 over the square root of 38 times j plus 9 over the square root of 38 times k as our final answer there. We could rationalize if we wanted to. If we wanted to rationalize this, we would have had the following. We would have had 13 root 38 over 38 times I minus 3 root 38 over 38 times j plus 9 root 38 over 38 times k if we rationalize. Pay attention to the problem on if they ask you to rationalize it or not. Most of the time, we're going to leave it up here because there's no need to rationalize them. Now, sometimes we got to do a little bit tricky stuff here. We got to just pay attention to what it's asking us for. It says find all values of a such that the vectors 7i plus 4j minus 6k and ai plus 4j plus 6k have the same magnitude. Okay, so if we take the magnitude of the first vector, I'm just going to call this v and this one w. So magnitude of v is the square root of 7 squared plus 4 squared minus 6 squared plus negative 6 squared. The magnitude of w is the square root of a squared plus 4 squared plus 6 squared. So in order for them to have the same magnitude, the magnitude of v must equal the magnitude of w. So the square root of 7 squared plus 4 squared plus negative 6 squared needs to equal the square root of a squared plus 4 squared plus 6 squared. So 7 squared plus 4 squared plus negative 6 squared needs to equal a squared plus 4 squared plus 6 squared. So in this case, 7 squared equals a squared. A is equal to plus or minus 7. Because the magnitude, so when you're squaring them, you can get the plus or minus in those senses. So make sure that we are remembering that whenever we do stuff.